Our next presentation is from Dr. Miles Dyck from the University of Alberta. He is presenting on effects of liming on soil health and soil and balance. Dr. Miles Dyck is a professor of soil science at the University of Alberta, researching the impacts of agricultural management on soil and crop health, and teaching courses in soil physics and soil formation. Growing up on the family farm near Swift Current, Saskatchewan, Dr. Dyck developed an intense curiosity about soils and an appreciation for the hard work required to run a farm. He is dedicated to executing and sharing results from farm-relevant research. Everyone, please welcome Miles.
Great, thanks. I appreciate the opportunity to come speak to you about some long-term research that I've had the privilege to be involved in at the University of Alberta Breton plots. They're located near the town of Breton, which is about an hour west of Leduc. It's southwest of Edmonton there, just to get you oriented. And we've been working with soil acidity and liming there for many years. Just to start, I'd like to acknowledge the many people that I've had the privilege to work with over the years, and that without their contributions, I wouldn't be up here speaking today. Students are always a big part of research and my research program. So Jadida Churcher is a current PhD student who's been working with me on the data that I am presenting today. My collaborator is Dr. Linda Gorham. She's the Western Grains Research Foundation Research Chair in Agronomy at the University of Alberta. And she started just over 5 years ago now, and I've been having a lot of fun collaborating with her. Dyck Praveen is our manager at the Breton plots, and so he's been there for over 25 years, and without him, we wouldn't have this rich data set. Dr. Jim Robertson is an emeritus professor, and his work over many years before I was around really made the plots a success. I work with a group of advisors on the Breton plots management team to help us make decisions about the continued management of the plots. And we have an endowment, and we have very many generous donors, which helps fund our activities at the plots. And in addition, we have other funders over the years, and currently ARDAR is funding me and Dr. Gorham for our research on soil acidity and liming in the prairies. So Alberta, we're the westernmost prairie province, and we have the largest acre of what we would call acidic or slightly acidic soils. So if you look at the map here, and the big green circles, those are those would be I'll just get my pointer here. Our major cities, right? So we're down here in Lethbridge, and so you can see a lot of the red are the most acidic areas, and blue is least acidic. So you can see that it's mostly in the northern half, the central and northern half of the part of the province where we have the most acidic soils. There's a few pockets down in the southwest corner here. And so the distribution of these soils, a lot of it has to do with the parent material these soils were developed on. So management does affect soil acidity, but it's mostly an inherited characteristic that comes along with the organic matter, and I'll talk a little bit about soil type in a minute. The big reason we're worried about soil pH and soil acidity in agriculture is that crop growth and crop health is affected by soil pH. And these are some textbook values for some of the major crops in Alberta, and gives you an idea of kind of what the optimum pH ranges are. And for most the main grain crops here and oilseed crops, 5.5 to 7, oats and some of the other grasses are more acid tolerant. And then the pulse crops and alfalfa are more sensitive to acidic conditions. So if we just jump back to the map here, we can see pH 5.5. So So we're not, even the most acidic soils maybe couldn't be considered to be in the danger zone for the major grain crops, but for the pulse crops and legume forages like alfalfa, there's potential there to have a yield impairment because of acidity. So pH, low soil pH or acidic pH impairs crop uptake of nutrients. It increases soluble aluminum in the soil, and aluminum is toxic to most crops above certain concentrations. Potentially increased susceptibility to disease. My colleague at the University of Alberta, Stephen Strelkoff, investigates clubroot, and they found that clubroot has high incidence on acidic soils, and that liming can help reduce the viable spore count in the soil. And soil acidity is often associated with low exchangeable basic cations like calcium and magnesium, and those cations do a lot to stabilize soil structure and soil organic matter. And when the soil is acidic, those stabilizing cations are generally low. And so there's lots of good information, extension information out there currently about soil pH and soil acidity. These are in the crop press by some famous folks like Ross McKenzie and Dr. Les Henry. And most recently in a December article in Top Crop Manager, which summarized some of the research that I'm involved in with Dr. Gorham. So I encourage you to search those out. There's some good information there. But today I'm going to be talking about our long-term research at the Breton plots. Like I said, the town of Breton is about an hour west of Leduc. And we have a long-term research trial there called the Breton Classical Plots, established in 1929. And so unlike North Dakota State there were exactly 0 statisticians consulted when we designed this experiment. So 1930 is the year when Fisher published his famous book. And so before then, concepts like replication and randomization weren't really on the minds of a lot of my predecessors. So our experimental design is a little complicated, and I'll go through that. But this, we have 2 rotations in this experiment, and one is a wheat fallow experiment. The other is a 5-year cereal-forage experiment, or rotation. And those are, the cereal crops are wheat, oats, and barley, and then 2 years of alfalfa brome hay. Barley is used as a nurse crop for the alfalfa brome. So the alfalfa brome is underseeded when the barley goes in, and so it's established for the following 2 years. And I'm just going to be talking about the 5-year rotation today, because that's where we have our liming treatments. So here's just to give you an idea of how the experiment is laid out. We have these kind of north-south oriented blocks. We call those series. And so on 5 of those blocks or series, we have the 5-year rotation. And the crops rotate through those blocks every 5 years. And so this was one of the, I think this last growing season, this was how the crops, the different rotation phases were laid out. So this is alfalfa brome year 1, and next growing season, this will be the 2nd year of alfalfa brome, and this, what was barley, this last growing season will be the 1st year of alfalfa brome, and so on. So that gives you an idea of how those work. Superimposed on those crop rotations, we have a variety of fertility treatments, and the ones I'll be talking about today are the check, which is a control. No fertilizer is applied there. I'll be talking about our full balanced NPKS treatment. That's all 4 macronutrients applied as fertilizers. We have a manure treatment, which is composted cattle manure. And then I'll be talking about this nitrogen exclusion treatment, where we apply phosphorus, potassium, and sulfur fertilizer, but exclude nitrogen. So you can kind of see our rates here. The rates of nitrogen are are low because we get quite a bit of N benefit from the alfalfa in the forage phase. 50 kilograms per hectare, which is close to 50 pounds per acre of nitrogen for wheat, 75 for oats, and 50 for the barley. And then in the hay phase, they don't receive any fertilizer for those 2 years. And our sources, we have kind of each source has only one nutrient in it, so we can exclude nutrients from certain treatments. And manure is applied to achieve an N application that's equivalent to the other nitrogen treatments over the 5-year rotation. So whereas with conventional fertilizers, we apply it every growing season, the manure is only applied before the wheat and before the oats, and to achieve 175 kilograms per hectare, same as the 3 cereal crops in the conventional fertilizer treatments. The soils at Breton plots are certainly different than the soils we have around Lethbridge. These were gray luvasolic soils, and they were developed in a boreal forest ecosystem, which is a lot different from Chernozemic soils, which represent the rest of the agricultural area in Alberta. So these two pictures kind of show the contrast. When these Chernozemic soils were broken and converted to agriculture, they plowed up these rich ribbons of sod with high organic matter and a lot of inherent fertility. When they cleared the boreal forest, in the boreal forest, all of the organic matter was in the forest floor on this mineral soil surface, and a lot of that got removed when the forest was removed, clearing for agriculture. So a lot different starting out farming on a gray luvasolic soil. So the topsoil has low inherent organic matter and low inherent fertility, but we found at Breton that these soils do respond to management quite quickly over time. So in the treatments I'll be talking about today, except for the check or the control treatment where we don't apply any fertilizer, we've seen a steady increase in organic matter since they were converted to agriculture. So we started out low, but there's a lot of storage potential. Just before I get into that, I want to show you, I forgot to emphasize that in our 5-year rotation, all of these blocks that are part of the 5-year rotation, they are split into east and west halves. And on the east half, we apply lime. And on the west half, there's lime is excluded, and it's been excluded since the beginning of the experiment. Lime is applied. We measure pH at least every 5 years, and when the soil pH falls below 6, we apply lime to bring the pH back up to 6.5. And except what you'll see recently, we haven't really, we've fallen a little bit behind, so we're due for another lime application, but this has actually resulted in some interesting data that I want to show you today. All right, so just to give you an idea on some of the how soil pH responds to liming. So this is our year on the x-axis, soil pH on the y-axis over the top 15 centimeters or 6 inches. This is from one of those blocks, Series A. And in the NPKS treatment, the red line is the limed treatment and the blue line is the unlimed treatment, just to give you an idea. And in this case, in the lime treatment, we applied lime in 1982 at a rate of 4,500 kilograms per hectare. In 2001, again, received 3,700 kilograms per hectare. And prior to that, before the data shown in this graph, there was a smaller amount applied. So you see the pH does respond to the lime application immediately, but I guess the old adage, what goes up must come down, is true in this case. And like I said, we're below our pH 6 threshold, so we're due for another lime application. But you can kind of see this steady decrease, and even since recent times, it's been fairly fast decrease in pH. So that's interesting as well. So that's just kind of one location over time. If we kind of average the different treatments over the since 1980, for this presentation, we see so the light blue here is limed and the dark is unlimed. Our treatments, the manure, the NPKS, the check treatment, and PKS. So you see that the unlimed half in the treatments with synthetic fertilizers, the pH decreases the most because basically as the microorganisms transform those fertilizers into plant available nutrients and they react in the soil, it produces acidity. So that kind of on top of all the other natural processes that occur in the soil that produce acidity results in the lowest pH values. So we see that at least over this kind of 43-year time period, though, that the liming treatments have had consistently higher pH. And even without lime, the manure, we've had that increase of organic matter from manure has done a good job of buffering the decrease in pH. Okay, so we're going to talk about the cereal crops in the rotation, the wheat and the oats, and to see if there's any liming effects on the yields. And so the yield, the differences in yields between the limed and the unlimed halves of the fertility treatments are not as dramatic as the soil pH. And that kind of jives with some of those optimum ranges that I introduced on the first slide. So we see the wheat yields don't really start dropping off until the pH falls below 5.5. And for most of this period, even in the unlimed half, the pH has been above 5.5 until the last few years. Where we do see a bigger difference for the wheat is with the nitrogen uptake. So this graph is, we have the treatments on the x-axis, and on the y-axis we have the amount of N recovered in the grain and the straw at the time of harvest and converted to kilograms of nitrogen per hectare. And so the light green is the unlimed and the dark green is the limed. And this straight line, this arrow here, that's 50 kilograms of nitrogen. That's the fertilizer that's applied. Okay, so the crop is accessing nitrogen from the fertilizer, but also a lot of nitrogen from the soil as well. And in the NPKS and the PKS, the treatments with the synthetic fertilizers, the difference in nitrogen uptake between the limed and the unlimed halves are the largest differences. Oats is typically more of an acid-tolerant crop, so we don't see significant differences in the oat yields in the lime and the unlimed halves there. These yields are in kilograms per hectare, but I did do a quick conversion up here if you want to convert those to bushels per acre. So basically every major tick there is 30 bushels per acre. And on the wheat graph there, every major tick was 15 bushels per acre. Right, so we see the effects of the overall fertility treatment, but we don't see any real differences between the limed and the unlimed subplots between treatments. And with the N uptake with the oats, again, not as dramatic as the wheat. Moving on to the hay, this is where things start to get a little more interesting. This is the hay yields, the total above ground hay yield just for the first cut. And so we see bigger yield differences between the limed and the unlimed half, especially in those treatments with synthetic fertilizers. And then we do, we separate the different components of our harvest samples as well. So our forage is a alfalfa brome mixture. So we do separate, in our harvest samples, we separate out the alfalfa or the legumes. And there's also a lot of volunteer clover. So it's not just alfalfa in terms of this legume yield, but it's a much greater difference for the limed and the unlimed half, just for the alfalfa component of the forage compared to the total above ground forage. So that makes sense in terms of the sensitivity of alfalfa. It's much more sensitive to acidic soils than than wheat or oats, as I showed on the first slide there. Okay, so that's the apparent effects of pH on yield. And so the title also mentioned N balance. The title mentioned soil health, but I ran out of time, and I'm running out of time here too. So we'll have to save soil health for another day. But you can see for the total soil nitrogen stocks in the top 15 centimeters, this is megagrams of N per hectare. We don't see a lot of difference in terms of the lime and the unlimed half of the treatment. Okay, so we see difference in yield. So there is certainly difference in the amount of N exported. There's a difference in, so let's just take wheat for example. In the limed half of the NPKS treatment, the above ground N uptake is around 115 kilograms of N per hectare. In the acidic half that doesn't receive any lime, it's around 95. So there's a difference of 20 kilograms of N per hectare. And that wheat is accessing nitrogen from urea and from mineralized soil organic nitrogen. And a big component of that, and this is where the lime has the biggest effect, is the biologically fixed nitrogen from alfalfa. So my last data slide here is these three graphs. This is the legume yield and the wheat N uptake and the soil nitrogen. So the biggest effect of the liming and the soil acidity is in this increased alfalfa survival on the limed half. That provides more nitrogen for the subsequent wheat crop. And even though there's more nitrogen exported with the higher wheat yields and wheat N uptake, the soil nitrogen levels still stay the same. Okay, so that increased N export in the wheat is offset by the increased nitrogen fixation in the alfalfa. And that's where the liming has the big effect. So in this case, if we're talking about liming effects, we have a direct effect of liming and soil pH on the alfalfa in the forage hay phase of the rotation at this place, at this site, in this example. And on the cereal crops, the liming effect is indirect. So it's not that the soil pH is reducing the yields in the wheat and the oats. It's the effect of this pH on the alfalfa and the biological nitrogen fixation of the alfalfa that's affecting the cereal crops. So in terms of extension to real fields, so if your rotation includes pulses or legume forages, managing your soil pH is very important. If you're just doing cereals and oil seeds, certainly managing pH is important, but you have a little more wiggle room there. So if you really want to get that nitrogen benefit from your pulses and your forage legumes, managing soil pH is very important. So that's it's been a pleasure to be able to share this with you today. And this is my email address and Linda's email address. If you have any questions, I encourage you to contact us. And if I haven't talked too long, maybe I can answer a question or two now. Thank you.
Thanks, Miles. I guess first a clarifying question on the wheat yield. You weren't necessarily seeing much of a yield difference. Is that correct?
Yeah, a small difference. Yeah.
Okay.
But not
so you're increasing your N export. So did you guys measure protein or anything like that?
Yeah, we measure total nitrogen in the grain, which we can convert to protein. But yeah, there is a bump in protein in the grain for sure. Yeah. Good question.
Any last questions?
With your liming over the past, how many years? Long?
Yeah, 40, 50 years. Yeah.
Have you seen a significant cost increase in that liming?
Yeah, I mean the product that we use, egg lime, by the way, I should have mentioned that. Yeah, the product prices increase. It's not a huge part of our budget because our plots are like a few acres, so it's not a big expense. But yeah, I mean, if you're looking at large scale, like quarter section scale, right, applying those rates of lime is very, very costly. And so lime is kind of a tough sell because you're doing something to avoid something bad. You're not going to apply lime and see a yield benefit the next year, right? You're going to apply lime to make sure you don't have yield losses in the long term. So it's a tough sell. Yeah, for sure.
Gonna check Slido quickly since you have 1 minute.
Okay.
Does not look like anything. Thank you
Okay.
very much, Miles.
Thanks a lot.